All right. Thanks. Okay, so I'm going to be talking about thermal atmospheric escape driven by high energy radiation. A lot of us here in the audience are interested in atmospheric escape, and the reason for that is that it's become clear that the atmospheres of relatively low mass planets are going to be substantially affected by escape processes. So just for example, if we wanted to think about a definition of the difference between a mini Neptune and a super Earth, we might define a mini Neptune as something that had a primordial hydrogen envelope accreted from the protoplanetary nebula, whereas this maybe a super Earth would be something that had its atmosphere primarily coming from outgassing. And if we want to ask questions kind of like this, then we need to understand escape processes. All right, so there is some evidence in the planet population for escape affecting planets close to their stars. We heard about the super Earth desert, and Eric or James may talk about this later, so I'm going to leave that to them. What I would like to talk about today is the physics behind thermal escape and a framework that I'd like to propose for organizing, understanding what regime of escape a particular planet might be in. So just for terminology, because I think particularly across these two communities, sometimes the words are used a little differently. This is what I mean. We have two classes of escape mechanisms. Each can be thermal or non-thermal. So you can have kinetic escape. I mean by that loss to space of individual atoms. So there's some height above the in the atmosphere called the exobase, above which individual atoms can escape to space. Or you can have hydrodynamic escape. In this case, you have bulk outflow from the planet of a collisional fluid. Right? So either of these regimes can be thermal. So thermal escape is driven by heat, hence thermal. And so the kinetic version of thermal escape is Jeans escape, where you have individual atoms at the high end of the Maxwellian tail of the velocity distribution escaping to space. And we call thermal hydrodynamic escape hydrodynamic escape. So this is being driven by pressure gradients in the atmosphere that's blowing a collisional outflow. And I'll talk about that a little bit more later. So you can also have non-thermal processes. A lot of these kinetic non-thermal processes, often mediated by magnetic fields, are important for solar system planets that are losing atmosphere at a relatively low rate. You could also have non-thermal hydrodynamic processes. For example, you could have Roche-Loeb overflow. You could have ram pressure stripping by a very intense stellar wind. So I'm going to be talking about these top two: thermal escape, Jeans escape on the kinetic end, and thermal hydrodynamic escape. All right, so what about the high energy photon part of this? So thermal escape is driven by ionizing photons. Actually, it could be driven by a lot of things, but this is the main process that we talk about, and it's the one I'm going to be talking about. Usually EUV, in some cases it could be X-ray, and what ends up happening is first you have a hydrogen atom, your high energy photon comes in, it ionizes your atom, your electron goes off with some extra velocity, it collides with nearby atoms, distributes that extra energy, and that gives you heat. So that's where the heating is coming from. It's photoionization heating. And the reason this is important is not that there's a lot of energy in the XUV coming from most stars compared to in the optical, for example. I mean, in the sun, 10 to the minus 6 of its luminosity is coming out in the EUV compared to the bolometric flux. The reason this is important is that there's a large cross-section for this process. So these photons are being absorbed way up high in the atmosphere. And so if they can effectively heat the thermosphere, it's the thermosphere because it's being heated by these photons. That's why it's hot. Then it can actually heat that layer of the atmosphere very hot and, for our purposes, drive escape. OK, so, and again, that's because of its large cross-section. All right, so just for clarity, what I'm going to be talking about today is not the atmospheric escape of water, for example, that determines whether you're in the habitable zone. I'm going to be talking about escape of the bulk component of the atmosphere. On Earth, water is not the bulk component of our atmosphere. Whether water from the ocean can get up to the thermosphere and escape is limited by diffusion. And so that tells you whether you're going to lose all your water and whether we're in the habitable zone. On the other hand, if you put water up in the thermosphere, it will escape right away. So just to relate to what we were talking about this morning, if you have a catastrophic runaway greenhouse, you fill your whole atmosphere with water, then it all will escape because it's no longer being kept at the surface, limited by diffusion. Okay. All right, so I showed this yesterday. I'm going to start with a tale of two thermospheres, both heated primarily by 15 to 20 EUV photons. So these are just above the photoionization limit for hydrogen. So in the current Earth Venus, we said that EUV absorption in the thermosphere leads to conduction of heat lower in the atmosphere, which is then radiated away by carbon dioxide 15 micron emission. Whereas for current hot Jupiters, that same EUV is absorbed and it leads to a collisional fluid outflow. So so how can we tell, whether you're going to get this sort of atmosphere or this sort of atmosphere or thermosphere or another type? So let's first look at thermospheric energy balance. So here's a plot for Venus. Here's degrees per Earth day on the x-axis, and this is a scale height on the y-axis. On the right is the heating processes, and on the left is cooling. So here you can see that in the bottom part of the atmosphere you have infrared heating. Once you get high enough, you have EUV heating. This is the part of the atmosphere we're talking about, the thermosphere. And for most of that part of the atmosphere, nope, doesn't work anymore. I'll just jump around. For most of it, it's actually being cooled by conduction, going down lower. And where it becomes collisional enough for carbon dioxide 15 micron radiation to cool, that becomes the dominant coolant. And that cooling layer is actually at the mesopause, as we've heard several times so far. So that's what tells you where the bottom of the thermosphere is. So on the other hand, for HG 209458b, which is an old hot Jupiter, there are a lot of curves here, but ignore most of them. The solid one is photoionization heating, and this dashed curve here is PDV work. So this is basically saying that almost all of the energy that's coming in is going into just pushing this atmosphere out in a bulk outflow. And a little bit of it near the bottom is coming out in Lyman alpha line cooling, but not a lot for that one. All right, so to say this the third time for Earth, here we have our troposphere, our stratosphere. This is the ozone absorption going up to the mesopause, and then you have this big, oh, thank you. And here you are in this very hot thermosphere. This is where the EUV is being absorbed. Here's where it's being conducted down. Here's where it's being dense enough that it's being radiated away by carbon dioxide. Whereas for a hot Jupiter, we have a different structure. Let's look at above, still way up high in the atmosphere, at something like nanobar pressures. You reached optical depth 1 for absorption of those high energy photons. And above that, you drive a hydrodynamic wind that gets up to 10 to the 4 Kelvin. So you go through a sonic point, and I'll explain where this is coming from in a moment. In the lower atmosphere, you're molecular hydrogen, but in the upper atmosphere, you've been dissociated into atomic hydrogen, and eventually you escape from your Roche-Lobe radius, which is where the distance to which your atmosphere can be bound to the planet. And your exobase, where you would be able to kinetically escape, is beyond that. So once you've gone beyond the sonic point, you're moving supersonic speeds. You can't shout upwind in a supersonic flow, so it doesn't care about the exobase at all. There's no kinetic processes here. It's all a fluid outflow. Okay, so what generates a Parker wind? If you're not familiar with the Parker wind, just to go through the SOT process, let's imagine first that we have a fluid. It's collisional. It's isothermal. You try to write down a hydrostatic atmosphere out to infinity. You can do this yourself. Your pressure at infinity will be greater than 0. This is bad because it means that it will be accelerated outward. So in this case, the energy for the work that's going on here is coming from this isothermal assumption. So we're not going to be able to keep that, but it's still worth thinking about this as a thought experiment. So now you have a velocity pushing this outward. This velocity will flow through a critical sonic point where the escape velocity is comparable to the sound speed. This is like the De Laval nozzle that allowed the Saturn V rocket to go up really fast. There's a critical point in the flow, and that the outflow has to go through unless it's confined by an external pressure. Otherwise, you'll divide by 0 and the equations won't work out. But basically, physically, what's going on is that your pressure is always greater than 0 at infinity, and so it keeps accelerating you until you eventually become supersonic. And the way this works out is that you have the sonic point is at a radius that goes as 1 over the sound speed squared. So as your temperature goes down, I'm just problematic here. Okay, as your temperature goes down, that radius goes up, so it takes you farther and farther to go supersonic. Below the sound speed, you're basically a hydrostatic atmosphere, so your density is dropping off exponentially. So even though your sound speed is going down, so your mass loss rate goes down in the flow as your temperature goes down. But also, you have to be collisional farther and farther and farther away from the planet in order to maintain a collisional flow out to where you're supersonic. Thank you. All right, so let's drop the isothermal assumption. Now, in a more realistic atmosphere, you have heating from photoionization. That's setting the lower boundary condition. The pressure at about nanobars is set by where optical depth is 1, photoionization. Heating, you still assume that this fluid that's here. You still assume that it's collisional, and you can get a nice outflow solution. It takes some work to actually get the solution, but you can do it. And for very high fluxes, you end up actually having ionization recombination balance at the base, just like an H2 region, for those of you who are familiar. Okay, so that's a Parker wind. But there are a few more thermospheres that it's worth considering, just for our purposes today. Early Earth-Venus has been considered, where you have strong EUV absorption, strong enough to conduct a lot of heat lower in the atmosphere that cannot be radiated away effectively. At least this is what the model does. Thanks. And that leads to a collisional fluid outflow from higher up. So this actually leads you to an escape from higher up in the atmosphere that increases your escape rate compared to what you would get if you didn't consider conduction. And early hot Jupiters, perhaps X-ray absorption leads to metal line emission, and you'll have both radiative cooling and a collisional fluid outflow. Okay. So I don't have time to go into this in detail. I'm happy to talk about this with anyone who's interested. But there's a classic paper by Watson that considers conduction for the early Earth. It's basically giving you that puffiness that I talked about. I'm worried about the collisionality in those models. Whereas Ben modeling showing that radiative cooling is important at both high or low fluxes. But here's the way I suggest that we think about this. We need to follow the energy. So we're depositing this energy in the thermosphere. And what can happen to it? It can be radiated away in place. That can happen for hot Jupiters orbiting T Tauri stars. You'll have a lot of it going out in either metal line cooling or Lyman alpha, plus an outflow. It can be conducted lower in the atmosphere, then radiated away, as for Earth and Venus. Or it can drive an outflow, which may or may not be energy limited, as for hot Jupiters or the early Earth and Venus inflated by conduction. So why isn't it easy to just calculate this? The reason is that the temperature and the escape rate are coupled in your atmosphere. So as you're outflowing your atmosphere, you're doing work on it, so you're changing its temperature. So if you want to calculate your outflow rate, you don't know your temperature to begin with. So if you don't know what regime you're in, this is what I think that you can do. So if we write down Jean's escape, hydrodynamic winds, and this is immediate blow-off. This is when you're so hot that basically your thermal velocity is the escape velocity from your planet at your surface. We can actually write this down as a single curve if we do it in the following way. So we can normalize the temperature of our thermosphere. So I'm assuming that there's a temperature for our thermosphere. It's roughly isothermal, but I'm being agnostic as to what that is. And I'm going to write that temperature as a thermal velocity normalized to the escape rate from the planet. And I'm going to use that as a parameter. I don't know what the temperature is. It's a parameter. And then I'm going to calculate a normalized mass loss rate based on this parameter. And the only thing I have to pick is the ratio between the collisional cross-section in the atmosphere, and the absorption cross-section for the high-energy photons. And that tells you where you transition from a wind to Jeans escape. That tells you where you're depositing your energy, how high your atmosphere stays collisional before things start becoming kinetic. That's the only parameter. So we can write down this single curve, and then I'll just show you what we can do with it. Now for a particular system, and this just has a break in it because it's an old version, I can non-dimensionalize it, put in dimensions, and plot mass loss rate as a function of temperature. And now I can say, well, let's imagine that there is no radiative cooling, there's no conduction. What would the energy limited mass loss rate be here? This is for a hot Jupiter. And it puts it up at something like 10 to the 4 Kelvin in the Parker wind regime. Now I know that that's a temperature that won't necessarily have strong radiative coolants. And it's self-consistent chemically if I do this for atomic hydrogen. So basically I'm done. I can do the same thing for Earth and get myself into the Jeans regime where conduction is important. And then I know that I have to redo my calculation, including conduction. Okay. So there's additional physics here. You have to put in tides, dissociation, ionization, chemistry. This slide is just to say that this framework doesn't absolve you from actually thinking. You still need to know what's going on in your atmosphere. But once you've thought, now you can go ahead and do this for any atmosphere that you like and get the framework for the escape from that atmosphere that you need to know in order to do a more detailed model. So this is an example for 6 Earth masses and 2.7 Earth radii. At fluxes from the current sun at 0.05 AU, you end up with an energy-limited hydrodynamic wind, mostly atomic hydrogen, no significant puffing or radiative cooling, large mass loss rate, 1% over 5 gigayears. At 1 AU, Jeans escape, tiny mass loss. The details of what the outcomes here aren't important. Oh, I just wanted to point out, this has to be H2. The point is, if you go through this thought process, you can end up with what regime you think you should be in. So here, for example, there's little radiative cooling, so it's too hot for H2. You need atomic hydrogen in this same planet around a young sun. Okay, so this is the idea. For any planet that you're thinking about, you consider the composition that you want. You can put in your temperature versus your mass loss rate, find where energy limited escape would put you on this plot, decide if it's too hot or too, for what your assumptions, decide if radiative cooling and conduction are important, and redo your model. So I'll just end by saying that there are a lot of other pieces of physics that can go into these calculations, for example, magnetic structure, stellar wind interactions. I've been working on 3D modeling of outflows from hot Jupiters with Caitlin Crater and John McCann, as well as Anjali Tripathi. So Caitlin and John are in the audience. I know James Owen has also been doing that. The reason that some of these 3D models are very important is that we need better observational diagnostics of escape. I've told you what I think is going on, but the actual observations that tell us about escape processes are pretty limited. We have, I think I'm out of time here, so we have uncertain measurements of Lyman alpha absorption. We have uncertain measurements of isotope ratios on Earth, and the planets in our solar system are losing mass at a low rate. So we really don't have any good observational diagnostics to say that really anything that I just said was correct. So that would be nice to do better on. Okay, thanks. Yeah. Yep. So normalized to things that we know, like, let me see if I can recover it off the top of my head. But it's normalized to, I mean, in here is the mass of the planet, I think there's the escape velocity is in here, and then We need, what else do we need? It's all things that we know.
Okay. You're not,
like observable things.
Okay, you're not having to make some assumption on your clues?
Nope. Nope. Observable things. I'll double check and tell you exactly what it is later. Yep. So this is, right, so these are all isothermal solutions. So this is a temperature as a function of temperature. So what the goal here is to figure out what the temperature is. And the goal is to figure out what the temperature is under the assumption that it's energy limited, and then decide if you really think it's energy limited. Because often you'll get an answer that's ridiculous, and then you know it's not energy limited, and you know you have to include coolants and or conduction. Yep. That's exactly what this is in. So this tells the distinction between the wind and the Jeans escape is you're only a wind if you're collisional to the sonic point. If you're not collisional to the sonic point, you are not a wind. You're in Jeans escape. And the little bit here is that I've taken, there's like a little bit of this phase space where I've done a velocity modified boosted Jeans to make these match nicely. But if, for example, your collision cross-section versus your absorption cross-section were different, then you would be a wind a little out further and then Jeans. So you'd have a different profile. This is not the same curve as this. This is, and the limit between them is whether you're collisional out to your sonic point. So it's of course sensitive to, it's of course at least a little bit sensitive to the isothermal assumption. But I guess what I would say in response to that is if you're in a regime where you're going to drop off dramatically until you get to the sonic point, I think you're already in the Jeans escape regime. So you know, there may be some cases where you need to do a little better than this. But the point is that the point of this isn't to have it be the final model. The point is to say what kind of atmosphere are we talking about at all? And then if you want to know the details, you can go do the detailed modeling.
So I think on the plot that came after this, you had a Parker with where as you went up in temperature, there was a maximum in the mass loss, and then it kind of turns around to the left. Why is, as you increase in temperature, the mass loss goes down as you turn around, so why is that?
Yeah, so that's because this is an old version of the plot where I didn't cut it off appropriately at this. I didn't put in appropriately this immediate blow-off regime. So you can see that the wind solution formally turns over, but what really ends up happening is you've reached the point where your thermal velocity is about your escape velocity. So what really is going to happen is it should just asymptote. That's right. And I think in the later ones, I had fixed that. Let's see. In these other plots that I made with the later version of my code, it had been fixed. Of which individual atoms can escape to space. Or you can have hydrodynamic escape. In this case, you have bulk outflow from the planet of a collisional fluid. Right? So either of these regimes can be thermal. So thermal escape is driven by heat, hence thermal. And so the kinetic version of thermal escape is Jeans escape, where you have individual atoms at the high end of the Maxwellian tail of the velocity distribution escaping to space. And we call thermal hydrodynamic escape hydrodynamic escape. So this is being driven by pressure gradients in the atmosphere that's blowing a collisional outflow. And I'll talk about that a little bit more later. So you can also have non-thermal processes. A lot of these kinetic non-thermal processes, often mediated by magnetic fields, are important for solar system planets that are losing atmosphere at a relatively low rate. You could also have non-thermal hydrodynamic processes. For example, you could have Roche lobe overflow. You could have ram pressure stripping by a very intense stellar wind. So I'm going to be talking about these top two: thermal escape, Jeans escape on the kinetic end, and thermal hydrodynamic escape. All right. So what about the high energy photon part of this? So thermal escape is driven by ionizing photons. Actually, it could be driven by a lot of things, but this is the main process that we talk about, and this is the one I'm going to be talking about. Usually EUV, in some cases it could be X-ray, and what ends up happening is first you have a hydrogen atom, your high energy photon, for escape affecting planets close to their stars. We heard about the super Earth desert, and Eric or James may talk about this later, so I'm going to leave that to them. What I would like to talk about today is the physics behind thermal escape and a framework that I'd like to propose for organizing, understanding what regime of escape a particular planet might be in. So just for terminology, because I think particularly across these two communities, sometimes the words are used a little differently. This is what I mean. I have two classes of escape mechanisms. Each can be thermal or non-thermal. So you can have kinetic escape. I mean by that loss to space of individual atoms. So there's some height above the in the atmosphere called the exobase above. All right, thanks. Okay, so I'm going to be talking about thermal atmospheric escape driven by high energy radiation. A lot of us here in the audience are interested in atmospheric escape, and the reason for that is that it's become clear that the atmospheres of relatively low mass planets are going to be substantially affected by escape processes. So just for example, if we wanted to think about a definition of the difference between a mini Neptune and a super Earth, we might define a mini Neptune as something that had a primordial hydrogen envelope accreted from the protoplanetary nebula, whereas this maybe a super Earth would be something that had its atmosphere primarily coming from outgassing. And if we want to ask questions kind of like this, then we need to understand escape processes. Right, so there is some evidence in the planet population comes in, it ionizes your atom, your electron goes off with some extra velocity, it collides with nearby atoms, distributes that extra energy, and that gives you heat. So that's where the heating is coming from. It's photoionization heating. And the reason this is important is not that there's a lot of energy in the XUV coming from most stars compared to in the optical, for example. I mean, there's in the sun, 10 to the minus 6 of its luminosity is coming out in the EUV compared to the bolometric flux. The reason this is important is that there's a large cross-section for this process. So these photons are being absorbed way up high in the atmosphere. And so if they can effectively heat,